Testing, testing. Mic is working, I think. Alright. Good time of day. Whether it's morning, evening, afternoon, night. It's a lovely winter. I mean, it's not really winter, but it's fall. And I had a really hard time deciding to come here and do this stream because it's easier to do something lazy, and for me this isn't lazy. So yeah, I feel like I should congratulate myself for that. Sharing. Yep, that's my screen. Okay. Ooh, look at me grow bigger. Okay. Yep, let's do the recap, the usual recap. Welcome to the stream if you're new here, and if you're not, thanks for being here. We are doing a course called Introduction to Machine Learning. That's on the fast.ai website, and it's taught by Jeremy Howard. And this is, if you see the title, this is like stream number 22. And in the past streams we have gone through lessons 1 through 7, and yeah, I can say that I am not like taking it as seriously as I should, but it's fun. I like it. Yeah, and today I'm gonna start lesson 8. Up until now it's been about random forests, and in lesson 7 we had a little part about gradient descent, but I think this time we are diving into gradient descent and logistic regression. So that's gonna be fun. Yeah, it's cool if I'm just starting lesson 8, but if I finish it, I am 2/3 like done, which is cool. Yeah. Anyway, like I have very low energy today, so I'm sorry about that. Yes, but I am here because I want to be. Gradient descent and logistic regression. Today we start the second half of the course. Oh my god, half? Really? We're moving from decision tree based approaches like random forest to gradient descent based approaches like deep learning. This is exciting and interesting. I'm liking this. Our first step in this journey will be to use PyTorch to help us implement a logistic regression from scratch. I actually really like it when we make things from scratch. We'll be building a model for the classic MNIST dataset of handwritten digits. That's gonna be fun. So we're going to be dealing with images instead of text for now. Okay, let's do this. Hello. Yes, stream number 22. That's funny. Welcome, Mustafa. How are you? Today I just felt like just sleeping like forever. But I was like, I missed Saturday for reasons, and now I was like, I need to be here. So I'm here to study, I hope. Days like this, you just if I want to leave bed. So yeah, and I think today is going to be interesting, learning wise. I don't know me wise, stream wise, but learning wise, I think it's going to be fun. Aww. Yeah, for those who don't know, Rachel is the other half of the fast.ai founders. Isn't an about us part? Anyway, I love her. I was stalking her on Twitter the other day. Yeah. Anyway. Okay. Mm-hmm. And we said it can't see what's happening in the future. It can't know what it can't know, but it's really good at what it knows. Have you started the course of how we... Shoot, I'm sorry. Are you... which course? This course that I'm... Why can't you hear it? Oh my god, I just realized you can't see my screen. I'm sorry. Whoa. It's only been 2 minutes, so I can fix that. Let's see. Okay.
So I don't want to embarrass Rachel, but I'm very excited.
Can you hear it? Or you should be able to hear it better, right?
That Rachel's here. So this is Rachel, for those of you that don't know.
Yes.
She's not quite back on her feet after her illness, but well enough to at least come to at least part with this lesson. So don't worry if she can't stay for...
Thank you. Sorry about that. I mean, I was monitoring OBS, but it just didn't cross my mind because this is white and it was showing the this tab, which is also white. Yeah, my bad. Okay, but yes.
The whole thing. And I'm really glad she's here because Rachel actually wrote the vast majority of the lesson we're going to see. I think it's a really, really cool work. So I'm glad she's going to at least see it being taught, even if unfortunately she's not teaching it herself. So it's coming. Good Thanksgiving present. Best Thanksgiving present. So we're, as we discussed at the end of last lesson, we're kind of moving from the decision tree ensembles to neural nets, broadly defined. And as we discussed, random forests and decision trees are limited by the fact, in the end, that they're basically doing nearest neighbors, right? That all they can do is to return the average of a bunch of other points. And so they can't extrapolate out to, if you're thinking, what happens if I increase my prices by 20% and you've never priced at that level before, or what's going to happen to sales next year? And obviously we've never seen next year before. It's very hard to extrapolate. It's also hard if it needs to, it can only do around log base 2n decisions, and so if there's like a time series it needs to fit to that takes like 4 steps to kind of get to the right time area, then suddenly there's not many decisions left for it to make. So there's kind of this limited amount of computation that it can do. So there's a limited complexity of relationship that it can model, right?
Right.
Yes, Prince.
Can I ask about one more drawback of random forest that I feel? So if we have data as categorical variable which are not in sequential order, so for random forest we encode them and treat them as numbers. Let's say we have 20 cardinality and 1 to 20. So the result that random forest gives is like the split that random forest gives is something like less than 5, less than 6. But if the categories are not sequential, not in any order, what does that mean?
Yeah, so if you've got like, I don't know, let's go back to bulldozers, EROPS.
I didn't really understand the question. So if non-sequential categories, that was it. Let's see how Jeremy explains it.
EROPS with a C, OROPS, and I don't know, whatever, right? And we arbitrarily label them like this, right? And so actually we know that all that really mattered was if it had air conditioning. So what's going to happen? Well, it's basically going to say like, okay, if I group it into those together and those together, that like, that's an interesting break, just because it so happens that the air conditioning ones all are going to end up in the right-hand side. And then having done that, right, it's then going to say, okay, well, within the group with the 2 and 3, it's going to notice that it's furthermore going to have to split it into 2 more groups. So eventually it's going to get there. It's going to pull out that category. It's going to take more splits than we would ideally like. So it's kind of similar to the fact that for it to model a line.
So more data, more splits. And I mean, it's not like it costs a lot. It's really good at it. But why are we trying to be mean to random forests just because we're moving on?
Fine. It can only do it with lots of splits and only approximately.
So random forest is fine with categories that are not sequential also.
Yeah, so it can do it. It's just like in some way it's suboptimal because we just need to do more breakpoints than we would have liked. But it gets there. It does a pretty good job. And so even
even Jeremy isn't being mean to random forests. I like that.
Although random forests, do have some deficiencies, they're incredibly powerful, particularly because they have so few assumptions, they're really hard to screw up. And, it's kind of hard to actually win a Kaggle competition with a random forest. but it's very easy to get like top 10%. So in real life, where often that third decimal place doesn't matter, random forests are often like what you end up doing. But for some things like this Ecuadorian groceries competition, it's very, very hard to get a good result with a random forest, because like there's a huge time series component, and like nearly everything is these two massively high cardinality categorical variables, which is the store and the item, and like so there's very little there to even throw at a random forest, and the difference between every pair of stores is kind of different in different ways, and so there are some things that are just hard to get even relatively good results with a random forest.
Okay.
Another example is recognizing numbers. You can get like okay results with a random forest, but in the end, the relationship between like the spatial structure turns out to be important, right? And you kind of want to be able to do like computations, like finding edges or whatever, that kind of carry forward through the computations. So just doing a kind of a clever nearest neighbors like a random forest, turns out not to be ideal.
Not sufficient. Okay. So what is this number supposed to be down here? As a human, I'm having a hard time recognizing it. It's not 4, it's not 7, right? It's not 9. And that's only the ones that I can tell. It's 4, right? Because like look at this 4 and this 4. Anyway, let's see what the machine says.
So for stuff like this, neural networks turn out that they are ideal. Neural networks turn out to be something that works particularly well for both things like the Ecuadorian groceries competition, so forecasting sales over time by store and by item, and for things like recognizing digits, and for things like turning voice into speech. And so it's kind of nice between these two things, neural nets and random forests, we kind of cover the territory, right? I haven't needed to use anything other than these two things for a very long time. And we'll actually learn, I don't know in what course exactly, but at some point we'll learn also how to combine the two, because you can combine the two in really cool ways. So here's a picture from Adam Geitke of an image. So an image is just a bunch of numbers, right? And each of those numbers is
So
not
cool.
255, and the dark ones are close to 255, the light ones are close to 0. All right.
You can see how, I mean, this is just black and white. So you can see the numbers.
So here,
See? We have like full on black, and then full on white, and then grays.
is an example of a digit from this MNIST dataset. MNIST is a really old, it's like a hello world of neural networks.
Yep.
And so here's an example. And so there are 28 by 28 pixels. If it was color, there would be
Everything is 28 by 28, I see.
3 of these, one for red, one for green, one for blue. Okay. So our job is to look at, the array of numbers and figure out that this is the number 8, which is tricky, right? How do we do that?
Yep.
So we're going to use a small number of fast AI pieces, and we're gradually going to remove more and more and more until by the end we'll have implemented our own neural network from scratch, our own training loop from scratch, and our own matrix multiplication from scratch.
Okay, I think I should go and look for this lesson somewhere, because I need to try to follow along. Video, course notes. I mean, course notes aren't always. Oh, yeah, this is course notes. Code is also there. I like it. Oh wait, is that literally the same? Oh wow, class 4 to 8. Okay. So I should go and see if there is Fast AI Machine Learning 2018 Lesson 4, if I can find that on Kaggle. So Fast AI Machine Learning course Lesson 4. Not deep learning. I'm gonna... Did I find it? Oh yeah, that's it. I see MNIST. These people are amazing. This is making me even more lazy. This is a copy, yes. Thank you. And yeah. Wait, what are these images that are not showing? Okay, at least there's a source. I'm guessing it starts from here, not here. Okay, got it. Let's see.
So we're gradually going to dig in further and further. All right, so the data for MNIST, which is the name of this very famous data set, is available from here. And we have a thing in fastai.io called get data, which will grab it from a URL and store it from on your computer, unless it's already there, in which case it'll just go ahead and use it. Okay, and then we've got a little function here called load MNIST, which simply loads it up. You'll see that it's zipped, so we can just use Python's gzip to open it up. And then it's also pickled. So if you have any kind of Python object at all, you can use this built-in Python library called pickle to dump it out onto your disk, share it around, load it up later, and you get back the same Python object you started with. So you've already seen this, something like this with like pandas feather format, right? Pickle is not just for pandas, it's not just for anything, it works for basically nearly every Python object. So, which might lead to the question, well, why didn't we use pickle for a pandas data frame, right? And the answer is pickle works for nearly every Python object, but it's probably not like optimal for nearly any Python object, right?
I sort of think of pickling like zipping. When you share something, you just want it to be together, so you put it together.
So because like we were looking at pandas data frames with like over 100 million rows, we really want to save that quickly, and so feather is a format that's specifically designed for that purpose, and so it's going to do that really fast. If we tried to pickle it, it would have been taken a lot longer, right? Also note that pickle files are only for Python, so you can't give them to somebody else, whereas like a feather file you can hand around. Okay, so it's worth knowing that pickle exists, because if you've got some dictionary or some kind of object floating around that you want to save for later or send to somebody else, you can always just pickle it. Okay, so in this particular case, the folks at deeplearning.net were kind enough to provide a pickled version. Pickle has changed slightly over time.
Zipping, it turns it into binary, so it makes it faster to load. Yeah, but like visually, I like to see it that way. But yes, I haven't actually looked at what it does inside, but I have used pickle before for like creating something like a model and then loading it in another file and then using it.
And so old pickle files like this one, you actually have to, this was a Python 2 one, so you have to tell it that it was encoded using this particular Python 2 character set. But other than that, Python 2 and 3 can normally open each other's pickle files. All right, so once we've loaded that in, we load it in like so. And so this thing which we're doing here, this is called destructuring. And so destructuring means that load mnist is giving us back a tuple of tuples. And so if we have on the left-hand side of the equal sign a tuple of tuples, we can fill all these things in. So we're given back a tuple of training data, a tuple of validation data, and a tuple of test data. In this case, I don't care about the test data, so I just put it into a variable called underscore, which kind of by like Python people tend to think of underscore as being a special variable which we put things we're going to throw away into.
Temp file. I mean, a temp variable, yeah.
It's actually not special, but it's really common. If you see something assigned to underscore, it probably means you're just throwing it away, right? By the way, in a Jupyter notebook, it does have a special meaning, which is the last cell that you calculate is always available in underscore.
Oh.
But that's kind of
like clipboard?
a separate issue. So then the first thing in that tuple is itself a tuple, and so we're going to stick that into X and Y for our training data, and then the second one goes into X and Y for our validation data. Okay, so that's called destructuring, and it's pretty common in lots of languages. Some languages don't support it, but those that do, life becomes a lot easier. So as soon as I look at some new data set, I just check out what have I got, right? So what's its type? Okay, it's a NumPy array. What's its shape? It's 50,000 by 784. And then what about the dependent variables? That's an array. Its shape is 50,000. So this image is not of length 784.
Yeah.
It's of size 28 by 28.
Yeah.
So what happened here? Well, we could guess, and we can check on the website, it turns out we would be right, that all they did was they took the second row and concatenated to the first row, and the third row and concatenated to that, and the fourth row and concatenated to that. So in other words, they took this whole 28 by 28 and flattened it out into a
one-dimensional array?
single 1D
Vector?
array. That makes sense? So it's going to be of size 28 squared. This is not like normal by any means, so don't think like everything you see is going to be like this. Most of the time when people share images, they share them as JPEGs or PNGs. You load them up, you get back a nice 2D array. But in this particular case, for whatever reason, the thing that they pickled was flattened out to be 784. Okay. And this word flatten is very common with kind of working with tensors. So when you flatten a tensor, it just means that you're turning it into a lower rank tensor than you started with. In this case, we started with a rank 2 tensor, a matrix, for each image, and we turned each one into a rank 1 tensor, i.e. a vector. So overall, the whole thing, is a rank 2 matrix, a rank 2 tensor rather than a rank 3 tensor. So just to remind us of, the jargon here, this in math we would call a vector, right? In computer science we would call it a 1D array. But because deep learning people have to come across as smarter than everybody else, we have to call this a rank 1 tensor. Okay. They all mean the same thing, more or less. Unless you're a physicist, in which case this means something else, and you get very angry at the deep learning people because you say it's not a tensor.
Yeah, a tensor is a 4-dimensional object, isn't it? Or, I don't know, a higher dimension.
So, there you go. Don't blame me. This is just what people say.
Yeah, don't blame the messenger.
So this is either a matrix or a 2D array or a rank 2 tensor. And so once we start to get into 3 dimensions, we start to run out of mathematical names
Tensor is more generic term to vector. One-dimensional tensor are matrices. Tensors and matrices are two-dimensional tensors. Yes. That's in a way basic computer science. Vectors and matrices, which I'm not saying I'm good at them, but I've studied them. But yeah, I just, oh shoot, I think I actually confused the word tensor with tesseract. Okay, got it. Because we have TensorFlow, and for some reason my brain connected it with tesseracts.
Right, which is why we start to be nice just to say rank 3 tensor. And so there's actually nothing special about vectors and matrices that make them in any way more important than rank 3 tensors or rank 4 tensors or whatever. So I try not to use the terms vector and matrix where possible, because I don't really think they're any more special than any other rank of tensor. Okay.
So you could just say this dimensional array. That's it, right? 4-dimension, 5-dimension, go forever.
So it's good to get used to thinking of this as a rank 2 tensor. Okay. And
so he's going to be using the ranks. Got it.
And then
yeah, that's what I was thinking about. Tesseract, 4D. I thought object, but yeah, cube.
The rows and columns, if we're computer science people, we would call this dimension 0 and dimension 1. But if we're deep learning people, we would call this axis 0 or axis 1. Okay? And then just to be really confusing, if you're an image person, this is the first axis and this is the second axis. Right? So if you think about like TVs, 1920 by 1080, columns by rows. Everybody else, including deep learning and mathematicians, rows by columns. So this is pretty confusing if you use like the Python imaging library. You get back columns by rows, pretty much everything else.
That's messed up though. People agree between you or each other. I mean, yourselves. Because, yeah. It's rows and columns, that's it. What's with the image people?
Rows by columns. So be careful.
Be careful out there. It's a scary world.
Because they hate us. Because they're bad people.
Of course.
I guess.
I went through this confusion in my first computer vision project. Oh no. You didn't have anyone to protect you. You went to it blind. At least Jeremy Howard is here to cushion us against this big bad world.
I mean, there's a lot of just, particularly in deep learning, like a whole lot of different areas have come together, like information theory, computer vision, statistics, signal processing, and you've ended up with this hodgepodge of nomenclature in deep learning. Often, like, every version of things will be used. So today we're going to hear about something that's called either negative log likelihood or binomial or categorical cross entropy, depending on where you come from. We've already seen something that's called either one-hot encoding or dummy variables, depending on where you come from. And really it's just like the same concept gets kind of somewhat independently invented in different fields, and eventually they find their way to machine learning, and then we don't know what to call them, so we call them all of the above, something like that. So I think that's what's happened with computer vision rows and columns. So there's this idea of normalizing data, which is subtracting out the mean and dividing by the standard deviation. So a question for you. Do you, often it's important to normalize the data. so that we can more easily train a model. Do you think it would be important to normalize the independent variables for a random forest, if we're training a random forest?
What happened?
To be honest, I don't know why we don't need to normalize. I just know that we don't.
We don't. Okay. Does anybody want to think about why? Karen?
It wouldn't matter because each scaling and transformation we can have will be applied to each row, and we will be computing means as we were doing, like local averages, and at the end we will of course want to denormalize it back to give, so it wouldn't change the result.
I'm talking about the independent variables, not the dependent variable.
I thought you asked about dependent variables.
Okay, who wants to have a go? Matthew?
It might be because we just care about the relationship between the independent variables and the dependent variable, so scale doesn't really matter.
Okay, go on. Why do we only, like...
Because at each split point, we can just divide to see which...
What do you mean split point? This isn't decision tree.
Regardless of what scale you're on, what minimizes variance, and that would...
Right, so really the key is that when we're deciding where to split, all that matters is the order. All that matters is how they're sorted. So if we divide by the, subtract the mean and divide by the standard deviation, they're still sorted in the same order. So remember when we implemented the random forest, we said sort them, and then we completely ignored.
Jeremy Howard here for the rescue, yep. The convention is width height when speaking about an image which translates to dimension 1, dimension 0. It's a bit counterintuitive. It is. It's going to become second nature after some experience in computer vision, image processing and all. Actually, we had a subject called image processing. We used MATLAB to salt and pepper and all that. I don't remember much, but I don't remember because I suppose we had done matrix when we were taking image processing. It just was never brought up. Yeah. I mean, the difference. I never noticed it. Maybe we didn't focus on it, I don't know.
The values, we just said now add on one thing from the dependent at a time. So random forests only care about the sort order of the independent variables. They don't care at all about their size. And so that's why they're wonderfully immune to outliers, because they totally ignore the fact that it's an outlier. They only care about which one's higher than what other thing, right? So this is an important concept. It doesn't just appear in random forests. It occurs in some metrics as well. For example, area under the ROC curve, you come across a lot. Right? Area under the ROC curve completely ignores scale and only cares about sort. We saw something else when we did the dendrogram. Spearman's correlation is a rank correlation, only cares about order, not about scale. So random forests, one of the many wonderful things about them are that we can completely ignore a lot of these statistical distribution issues. But we can't for deep learning, because for deep learning we're trying to train a parameterized model. So we do need to normalize our data. If we don't, then it's going to be much harder to create a network that trains effectively. So we grab the mean and the standard deviation of our training data and subtract out the mean, divide by the standard deviation, and that gives us a mean of 0 and a standard deviation of 1. Now for our validation data, we need to use the standard deviation and mean from the training data, right? We have to normalize it the same way. Just like categorical variables, we had to make...
So we're just changing all the values? I don't really understand this point. Behave better when data is normalized. And that is when the mean is 0 and standard deviation is 1. Okay. I mean, I think this is actually easy because we have a bunch of numbers, but I don't know, because like normalization means different things in different places, right? Okay, I'm gonna accept it as it is because I sort of understand. And then worry about text when we get to the text lesson. For now, just a bunch of numbers between 0 and 255, but he updated it to be between 0 and 1. That's it, right?
Make sure they had the same indexes mapped to the same levels for a random forest. Or missing values, we had to make sure we had the same median used when we were replacing the missing values. You need to make sure anything you do in the training set, you do exactly the same thing in the test and validation set. So here I'm subtracting out the training set mean, the training set standard deviation. So this is not exactly 0, and this is not exactly 1, but it's pretty close. And so in general, if you find you try something on a validation set or a test set and it's like much, much, much worse than your training set, it's probably because you normalized in an inconsistent way or encoded categories in an inconsistent way or something like that.
Okay.
All right, so let's take a look at some of this data. So we've got 10,000 images in the validation set, and each one is a rank 1 tensor of length 784. In order to display it, I want to turn it into a rank 2 tensor of 28 by 28. So there's NumPy has a reshape function that takes a tensor in and reshapes it to whatever size tensor you request. Now, if you think about it, you only need to tell it about, if there are d axes, you only need to tell it about d minus 1 of the axes you want, because the last one it can figure out for itself, right? So in total, there are 10,000 by 784 numbers here altogether, right? So if you say, well, I want my last axes to be 28 by 28, then you can figure out that this must be 10,000. Otherwise, it's not going to fit. That makes sense? So if you put minus 1, it says, like, make it as big or as small as you have to make it fit. And so you can see here it figured out it has to be 10,000.
Okay.
So you'll see this used in neural net software, pre-processing and stuff like that all the time. Like, I could have written 10,000 here, but I try to get into a habit of, like, any time I'm referring to, like, how many items are in my input, I tend to use minus 1, because, like, it just means later on I could, like, use a subsample, this code wouldn't break. I could, do some kind of stratified sampling. If it was unbalanced, this code wouldn't break. So by using this kind of approach of saying, like, minus 1 here for the size, it just makes it more resilient to changes later. It's a good habit to get into.
Okay.
So this kind of idea of, like, being able to take tensors and reshape them and change axes around and stuff like that is something you need to be, like, totally do without thinking, because it's going to happen all the time. So, for example, here's one.
I'm not a vision researcher, so Jeremy, I'm not going to take this one too seriously, but thank you. I am going to learn about it, but I'm not going to have it be second nature.
I tried to read in some images. They were flattened. I need to unflatten them into a bunch of matrices. Okay, reshape, bang. I read some images in with OpenCV, and it turns out OpenCV orders the channels blue, green, red. Everything else expects them to be red, green, blue. I need to reverse the last axis. How do you do that? I read in some images with Python imaging library. It reads them as rows by columns by channels. PyTorch expects channels by rows by columns. How do I transform that? So these are all things you need to be able to do without thinking, like straight away, because it happens all the time, and you never want to be sitting there thinking about it for ages. So make sure you spend a lot of time over the week just practicing with things like all the stuff we're going to see today: reshaping, slicing, reordering dimensions, stuff like that. And so
reordering dimensions, that's a cool thing to say. like sci-fi novel about a guy, or gal, don't have to be a guy, a person, who's putting order back into the dimensions. So they're reordering the dimensions.
So the best way is to create some small tensors yourself and start thinking like, okay, what shall I experiment with? So here, can we pass that over there?
Do you mind if I backtrack a little bit?
Of course, I love it.
So back in normalize, you say, like, you might have gone over this, but I'm still like wrestling with it a little bit.
Yeah.
You say many machine learning algorithms behave better when the data is normalized,
Yeah.
but you also just said that scale doesn't really matter. So like,
I said it doesn't matter for random.
Yeah, for random forests. Sorry for pausing you, Jeremy. I'm just trying to answer you before you answer so that I understand that I am focusing and I'm not falling asleep.
Forests.
okay.
Yeah. So random forests are just going to split things based on order. And so we love them. We love random forests for the way they're so immune to worrying about distributional assumptions. But we're not doing random forests. We're doing deep learning, and deep learning does care.
The word for reordering dimension is, transposing with denser. I agree, reordering dimension. Yeah, it does. It's like bringing order back into the dimensions. But transposing means... Is that what reordering dimensions means? Because I know what transposing means. And, like, there's this method in MATLAB when we were like... I actually learned about transposing using images, but then you use it for rows and columns. You know, Excel sheets and stuff, so... Yeah. Thank you. Now I understand it better.
Yeah. Can you pass it over there?
If we have a parametric, then we should scale. If we have a non-parametric, then we should know to scale.
Yeah, basically. Transposing means swapping columns and rows, yes. Yeah, we use it when dealing with data.
Scale. Can we generalize?
No, not quite, right? Because like k nearest neighbors is non-parametric, and scale matters a hell of a lot.
I don't know what channels is. Rows, columns, and channels in 3D shuffle. Okay. I haven't dealt with it that seriously. Yeah. It's really not easy to visualize in your head.
Lots. Yeah. So I would say things involving trees generally are just going to split at a point, and so probably you don't care about scale. But you know, you probably just need to think like, is this an algorithm that uses order, or does it use specific numbers?
Can you please give us an intuition of why it needs scale? Just because that way may clarify some of the issues.
Not until we get to doing SGD. So we're going to get to that. Yeah. So for now, we're just going to say, take my word for it. Can you pass it to Daniel?
So this is probably a dumb question, but can you...
Channels is the RGB? Okay, thank you. Thanks for the explanation. Yeah, I know RGB NA. Yeah. We even had another subject on... I forgot exactly what it was, but we studied these... Yeah, I'm like, we did study stuff, huh? Yes, NA does mean alpha, you're right. Yeah, I just didn't know it was called channels. And that we're still talking about images and not just 3D, I mean, like arrays of three-dimensional arrays or matrices or, you know, just numbers. Well, images are just numbers, but yes, okay. Wow, so shuffling rows and columns and colors? That's cool.
Like explain a little bit more what you mean by scale, because I guess when I think of scale, I'm like, oh, all the numbers should be generally the same size.
That's exactly what we mean.
But is that like the case like with the cats and dogs that we went over with like the deep learning? Like you could have a small cat and like a larger cat, but it would still know that those were both cats.
Oh, I guess, this is one of these problems where language gets overloaded. Yeah. So in computer vision, when we scale an image, we're actually increasing the size of the cat. In this case, we're scaling the actual pixel values. So in both cases, scaling means to make something bigger and smaller. In this case, we're taking the numbers from 0 to 255 and making them so that they have an average of 0 and a standard deviation of 1.
Jeremy, could you please explain us, is it by column, by row?
By pixel. By pixel.
When
there's a single...
In general, when you're scaling, just not thinking about even a picture, but a kind of an input to a machine learning.
So, okay, method. Sure. So, I mean, it's a little bit subtle, but in this case, I've just got a single mean and a single standard deviation, right? So it's basically, on average, how much black is there, right? And so, on average, we have a mean and a standard deviation across all the pixels. In computer vision, we would normally do it by channel. So we would normally have one number for red, one number for green, one number for blue. In general, you need a different set of normalization coefficients for each thing you would expect to behave differently. So if we were doing like a structured data set where we've got like income, distance in kilometers, and number of children, like you need 3 separate normalization coefficients for those. They're like very different kinds of things. So yeah, it's kind of like a bit domain specific here. It's like, in this case, all of the pixels are, levels of gray. So we've just got a single scaling number. Where else you could imagine if they were red versus green versus blue, you could need to scale those channels in different ways.
Okay.
Can you pass that back, please?
So I'm having a bit of trouble imagining what would happen if we don't normalize in this case.
So we'll get there. So so this is kind of what Yannette was saying. Is like, why do we normalize? And for now, we normalize.
Heads up, I think I'm gonna end the stream after this question session, which is in 4 minutes, I think.
Because I say we have to. When we get to looking at stochastic gradient descent, we'll basically discover that if you, basically to skip ahead a little bit, we're going to be doing a matrix multiply by a bunch of weights. We're going to pick those weights in such a way that when we do the matrix multiply, we're going to try to keep the numbers at the same scale that they started out as. And that's going to basically require the initial numbers. We're going to have to know what their scale is. So basically, it's much easier to create a single kind of neural network architecture that works for lots of different kinds of inputs if we know that they're consistently going to be mean 0, standard deviation 1. That would be the short answer. But we'll learn a lot more about it. And if in a couple of lessons you're still not quite sure why, let's come back to it, because it's a really interesting thing to talk about.
Yes, I'm just trying to visualize the axes we're working with here. So under plots, when you write, so x valid shape, we get 10,000 by 7, 8, 4. Does that mean that we brought in 10,000 pictures of that dimension?
Exactly.
Okay. And then in the next line, when you choose to reshape it, is there a reason why you put 28, 28 on as y or z coordinates, or is there a reason why they're in that order?
Because we know the images are 28 by 28 pixels, because that's what MNIST decided, to make it simple and easy to work with.
Sure.
Yeah, there is. Pretty much all neural network libraries assume that the first axis is like, it's kind of the equivalent of a row. It's like a separate thing. It's a sentence or an image or a, example of sales or whatever. So I want each image, to be a separate item of the first axis. And then so that leaves 2 more axes for the rows and columns of the images.
And that's pretty standard.
That's totally standard. Yeah, I don't think I've ever seen a library that doesn't work that way. Can you pass it to Abira?
So while normalizing the validation data, I saw you have used mean of x and standard deviation of x data, training data only.
Yes.
So shouldn't we use mean and standard deviation of validation data?
You mean like join them together, or?
No, separately calculating mean?
No, because you see, then you would be normalizing the validation set using different numbers. And so now the meaning of like this pixel has a value.
It would be sort of like cheating, right?
Of 3 in the validation set has a different meaning to the meaning of 3 in the training set. It would be like if we had like days of the week encoded such that Monday was a 1 in the training set and was a 0 in the validation set. We've got now 2 different sets where the same number has a different meaning.
Oh.
So we want to make sure
it's about different meaning, not data leakage in a way.
Sure that we. So let me give you an example. Let's say we were doing like full color images, and our tests, their training set contained like green frogs, green snakes, and gray elephants. Right? We're trying to figure out which was which, and we normalized using each channel mean, and then we have a validation set and a test set which are just green frogs and green snakes. Mm-hmm. So if we were to normalize by the validation sets statistics, we would end up saying things on average are green, and so we would like remove all the greenness out, and so we would now fail to recognize the green frogs and the green snakes effectively, right? So we actually want to use the same normalization coefficients that we were training on. And for those of you doing the deep learning class, we actually go further than that. When we use a pre-trained network, we have to use the same normalization coefficients that the original authors trained on. So the idea is that, a number needs to have this consistent meaning across every data set where you use it.
Fair.
Can you pass it to Asmita?
That means when you're looking at the test set, you normalize the test set based on this mean set?
That's right.
Okay.
That's right. Okay.
Okay. Shoot. Chill. There. Yep. That was today. I survived. I did it. I made it. It was fun. We're just getting started. It was a bit of a review plus just some exploring, or just getting started. And that was 34 minutes of the of lesson 8. So yeah, thank you for today. We are inshallah going to be continuing because I need to because I need to learn better, and I need to, there's this silly idea that I have that is, so I need to learn something else, like the something else is just our language, which is like when someone's starting with, I would say data science, not exactly machine learning, but also machine learning, they normally choose between R or Python, right? And I chose Python, but then in my work we are using R little by little, and there's this competition coming up that I am hopefully able to join, that my team is using R and my R skills are not great. So I was like, I could do the what is it called? There's a book that's like, this is the Start with R book. So I was like, let me see if I can study that, but then I actually didn't, because like I had a few weeks and I still haven't done much. You want to learn R too? So here's the thing. Thank you. The thing is, I don't know, like, the thing that I am contemplating is, do I stream on YouTube or do I go to Twitch? Should I have, because like audience wise, both is fine. Oh yeah, free code camp? Okay. I like free code camp because I think they take, like with permission obviously, separate videos, turn it into one huge video. They even have the CS50 classes there. Yeah. So I think that one will be short because the competition is in November. And I think I might even be selective about where to start and what to do instead of starting from exact 0. But honestly, I'm not that good. Like, I was working with some data yesterday and I kept having to Google things and messing things up. So yeah. Yeah, I think my current concern is whether I should do it on Twitch or on YouTube. I don't know. I think it's easier for me to do it on YouTube because I have it all set up. I'll have to make a thumbnail for it. God, life is hard. But yeah, so I was thinking, now I stream every other day, which is easier for me, but I can now fill in those every other days with the R language. I am googling R language. There, yep. R language for data science. I think that's the book, isn't it? Yes. Let me go back to the screen while this is loading. Yeah? This is the book, right? This is created with... Nope. Not it. It's not this one. Because... Wait. What happened? Oh, there it is. Like, if you go to... Is that the book? Okay. Let's just say R language... intro something. Yeah. Which book was it that I was not you, Siran. Not this. Ugh. Anyway. R for data science? Isn't that the one I just opened? Yes, it was. Apparently it's this one. Anyway. Why is this different? Anywho, I'm gonna double check whether it's this one or not. Okay, see, this book is out of date. Let me... New Zealand. Yes, it's this one. Why do I know? Because the other one is created with Markdown, but this one's created with Quarto or whatever, I don't know. So yes, it is exactly this one. R for data science. It's a book, but if you go through it, you'll see that it has code snippets, because it's basically like a notebook, but you can't actually run it. So there's a really high likelihood that this has been taken somewhere where you can work with it as a notebook, and it's like on GitHub even, so that's fun. I'm gonna paste this here so that you can check it. Yeah, that is that. Okay, I gotta go. If my energy allows it, we might do R tomorrow. And I might do it, like I said, lazily, selectively. Don't depend on me for that one. Yeah. So that is it for today. Inshallah, maybe see you tomorrow. And have a lovely rest of your day. It's Monday, isn't it? Yes. Okay. Have a lovely Monday with blessings Mondays are a blessed day, aren't they? Garfield doesn't like them, but I like them. Okay, I'm gonna end the stream. Thanks for being here. I appreciate it. Happy learning. Okay, I'm gonna end it in 5, 4, 3, 2, and 1. We're gonna blast off and yeah, have a lovely day. Goodbye.